right, ladies and gentlemen, welcome back to another round of AP Chemistry Information. This is Mr. Doolin. I thank you for tuning in. Today we're going to take a look at galvanic cells. Galvanic cells are a type of electrochemical cell. So if you want me to spell that out, that would be electrochemical. They are a type of electrochemical cell. The thing that makes them unique, or a unique type of electrochemical cell, is that they are thermodynamically favorable. I'll write that out too. Thermodynamically favorable. Now, thermodynamically favorable is a really fancy term for saying that the reactions will occur spontaneously. All right? But I will go ahead and tell you that the College Board does not like that word spontaneous, and they will use the words favorable and thermodynamically favorable for your spontaneous reactions because students would always think that spontaneous meant that it would happen fast. That's not what it means. It just means it will happen on its own once the reaction gets started. Okay? So a galvanic cell is a thermodynamically favorable electrochemical cell. You probably know it as a battery. That's probably how you know it, okay? So this is what we're going to get into today. We're going to apply these oxidation, these reduction reactions, and we're actually going to learn how batteries work. All right, ladies and gentlemen, so I went ahead and paused the video and I erased everything, and now we're back and I've drawn a galvanic cell. So it's not that complicated, and what we're going to do is we're actually going to start labeling this together. Now, first thing I want you to notice is that we've actually got two different containers here, right? These are actually called your half cells. And so I have two half cells to make up my total overall galvanic cell. All right? A couple other things that we see. We've got this tube-looking deal in the center. This is called your salt bridge. And what the salt bridge does is it actually helps balance out the charge of the galvanic cell. So it helps balance out the charge. Generally, what's going to happen in here is we're going to have ions. We're going to have some kind of salt, some kind of ionic salt is going to be in here that's soluble, right? And we'll learn later on when we actually get to doing these problems which direction those salt ions actually flow. But the purpose is to balance out the charge. Remember, we're going to have a transfer of electrons here. This is going to be a redox reaction. And so if we have negative charges flowing towards one direction, we have to actually balance that out or we're going to have a buildup of charge, all right? Okay, and so the next thing we'll take a look at is we will label our electrode. Now, our electrode is a metal strip that normally goes into the solution that we're going to be dealing with, and what its purpose is to actually conduct the electrons. Right? It actually allows the electron to flow. Now, in this particular case, this is the reaction that we are taking a look at. And so one of my electrodes, if you notice here, this is solid zinc. And then the other electrode would actually be solid copper, the way that I've got this set up. All right? And that's Cu. So one of the electrodes would actually be solid copper. The other one would be solid zinc. All right? Okay. There is something called an inert electrode. It's called an inert electrode, and an inert electrode is not actually part of the reaction. It's a spectator. The only thing that it does is it actually just does conduct the electron flow. Okay? All right. The next thing is the red. The red is actually just a wire. The wire connects the two half cells, and electrons will flow in the wire. All right? Because, again, we need to have that transfer, right? Oxidation's loss of electrons, reduction's gain of electrons. We're going to have a transfer of electrons that occur here. Okay? All right, the next thing in the middle is a voltmeter, right? We will call the voltmeter, and the voltmeter will give us the overall cell potential. The voltmeter will give us the overall cell potential, all right? Okay, next thing what we're going to do is we are going to start labeling anode, the anode and the cathode. And this is the point where you have to bear with me for just a little bit. The other thing I'm going to do is I'm going to show ions in solution. Over here we've got copper 2 plus, copper 2 plus, copper 2 plus. On the other side we've got zinc 2 plus, zinc 2 plus. I want to write 2's every time. Zinc 2 plus. So I've got ions in solution. These are 1 molar. This is a 1 molar zinc nitrate solution. Remember, nitrates are soluble. They're going to be spectators here. We are not going to pay attention to them. Over here, I would have 1 molar copper nitrate solution. All right, and it's important to understand the molarity of this as being 1 molar. 1 molar and 25 degrees Celsius equals standard conditions. So my standards conditions are 1 molar, 25 degrees Celsius, not to be confused with STP. Please make that distinction in your head. All right. Okay, so now we're going to learn a couple of different things here. We're going to learn electron flow. So which way do electrons actually flow? If you notice, this is a 0 and this is +2, so electrons are flowing away from the zinc and towards the copper, right? If you actually just assign the oxidation numbers and you see that, hey, this is my reduction, and then this is my oxidation. So my electron flow, an easy way to remember electron flow, let me erase this pink line here, is actually the mnemonic called FAT CAT. And what this is from anode to cathode. Electrons always flow from anode to cathode. And this is because the other statement here, where do our reactions occur? And the mnemonic there is actually red cat. So it's a red fat cat. So red cat stands for reduction occurs at the cathode. Reduction occurs at the cathode. So my reduction reaction occurs over here at the cathode, right? My electron flow is going in this direction. If you notice, I have 2 moles of electrons going in that direction. All right? Okay, so that's a lot. You do need the vocabulary. You need anodes, you need cathodes, you need salt bridge, you need function of salt bridge, you need direction of electron flow, you need where reactions occur, you need what standard conditions are, you need what an electrode is, you need to know what an inert electrode is. All right, and then we'll get into a lot of this other stuff as we go on to different cells, but I do need you to understand that if you look at this reduction reaction, my copper is actually going to plate on here, so this electrode will get heavier. I hope you see that because we'll be plating out solid copper, and then over here my zinc ions are heading in that direction, so this will get lighter. So just one thing I want to put in there, all right? Okay, moving on. All right, so here we go. Now what we're going to do is in that last drawing that I had up here, if you can look on yours, on the voltmeter we actually showed an overall cell potential of 1.1 volts. And so now, how do we actually determine that overall cell potential? How do we determine the voltage of a battery? All right, and so what we're going to do is we're going to take a look at standard reduction potentials. Now, the reduction is important here because every reaction that I'm about to write is going to be written as a reduction reaction. All right, and so I'm looking here, this is the standard reduction of hydrogen. The standard reduction potential, and this is one of those things that we looked at, or scientists looked at, and they said, what are we going to compare everything to? Where's our starting point? And so hydrogen became our starting point. Every reduction potential that you're going to see is compared and relative to the standard hydrogen electrode. So all the numbers are just a relative number to how much more likely it is or less likely it is to be reduced than hydrogen, all right? And so the standard reduction potential of hydrogen is exactly 0. We set it to be that way, and then we're going to use it as a reference point and compare everything else to it. So the 2 standard reduction reactions that we're interested in today, because of the reaction we were looking at before, are zinc, the reduction potential of zinc, and that's a negative number. And then the next one is the reduction of copper. And this will be Cu, and that is 0.34. So, a couple of things to notice. Notice one of these is negative and one of them is positive. So a big thing that you need to get down about standard reduction potentials is that the more positive the standard reduction potential, the more likely it is to be reduced. So the more positive the standard reduction potential is, the more likely it is to be reduced. So if I'm comparing these two, then what I would say is that copper, if I'm going to have to pick, this is going to be my reduction reaction, which means this is my oxidation reaction. Now the problem with this is that the way the reaction is written is actually as a reduction reaction. And so going forward is reduction. That means going in reverse, if you look at it, is actually your oxidation reaction. And so what I can do is I can actually just rewrite this, go into zinc, and that should be zinc 2 plus, I left that off. 2 plus plus 2 electrons. Now it's an oxidation, and what we do is we actually turn the charge of that, or the sign of that, and make it a positive number. Now, I hope you notice if I actually add these two things together, that cancels out. I end up with Cu2 plus zinc, giving me zinc 2 plus copper. That was my original reaction, and then if I add these two things together, I actually get 1.1 volts. All right, so big things to take away here. Standard reduction potentials, the more positive they are, the more likely they are to be reduced. If you need it to be an oxidation reaction, all you do is write the reaction in the reverse direction, and then you change the sign of the reduction potential. All right, okay. That was a lot in 10 minutes. Hopefully you got it. If you got some questions, make sure you get it down. We will get those addressed in class, and I will see you there.